Okay, so I'm going to try and cover two things today. The first one I'm not going to say much about right now, but I just kind of want you to get into the what it's about thing. We're going to do linear regression, which is going to mean that we go back, so this is sort of review for the final two, compute the means, the standard deviations, the covariance, and the correlation, just like we did on the first test. But we're going to add to that as a t-test. So, you know, if your data look like that, you're going to get a t-test that's pretty high, and you're going to reject HO, which is no relationship, and say that there is a linear relationship. Whereas if you had something like that, that doesn't look as much like a line, so you would fail to reject HO and conclude that there might not be a linear relationship. So that's just, you know, we're going to work those in a minute, but I wanted to just say a word about it before we got going. Okay, so the first thing we are going to cover today is called the chi-square test. If you spell it out, chi-square test, and that's if you write it symbolically. And so basically in the chi-square test, what you have is two categorical variables. This might be male and female and color of car. Maybe red, white, and black seem to be fairly popular colors. And let's think of this way for right now. Let's suppose that I'm in some kind of big classroom or seminar or something like that, and I go out in the parking lot during a break, and I count in the parking lot, and I know everybody has driven their own car there. And I go out in the parking lot, and I count 60 red cars, 100 white cars, and 40 black cars. Then I count the number of males and females in the place, 100 of each. If there were no relationship between gender and car color, how many people would you expect to be driving, how many males would you expect to be driving a red car? 30. If there's no relationship, whatever this proportion here, I happen to have a 50-50 split, 100 males and 100 females, so I would expect 30 and 30. There's an even split of males and females, so I would expect, if there's no relationship. So this is HO. There is no relationship between gender and car color. So that's my hypothesis. No difference. It's just sort of like everything else. When you say mu A not equal to mu B, you're saying there's no difference. So here we're saying there's no difference or no relationship between these two categorical variables. And if we just had a 2 by 2 there, that just could be a 2 proportion z-test. So all we've done now is extend. Like yesterday we had gone from, we had earlier 1 mean, 2 means. ANOVA was 3 or more. Now we went from 1 proportion, 2 proportions, to many. And it's not tied to 2 by 3, you could have a four by 3 table, and this will still work, the process that we're going to do. So now let's say that we went out and we collected some data, and that this is what we observed now. Of course, this hasn't changed. The cars are still in the parking lot, and there's still 100 males and 100 females. But now, I sit out the window and watch people get in their cars, kind of like a spy game or something, And so I observed this. Let me change that. So let's just say we came up with those numbers. This is what I actually observed. Keeping with that, I guess, thought, let me go ahead and write here. This is what we expect if no relationship. So do you think there's a relationship? It looks like it, because these numbers are far from what you would expect if there's no relationship. In fact, that really is the same logic we've been using all along. It's a little bit, looks a little different, but I think maybe even a little easier to see. We've been saying that here's no relationship. Now, what does it look like if if we can say there isn't a relationship? It means they're far from what we'd expect if there's no relationship. So, for HR, I'm going to go back to that. There is a relationship between gender and car color. We'll call this example data 1. So let's just say, now that wasn't the data. That's one possibility. Let's say that we had this data. Actually, I'm going to show you a couple of things here. Okay, before I go on any further, this is degrees of freedom. This problem has 2 degrees of freedom, because now, once I've entered those 2 numbers, again, I've already looked out in the parking lot and I've counted the people in the place. Now, once I've actually gotten that there are 32 males in red cars and 51 males in white cars, everything else is determined, not free to vary. I know that this has to be 28, because there were 32 of these. This has to be 49. Let's see, that's got to be 17, and that's got to be 23. So when you do degrees of freedom for the chi-square test, I mean, the way I do it is, let's say if it was this problem over here, is just blot out one row and one column, so this one would have 6 degrees of freedom. Once you have 6 numbers in there, and you know what's out on the margins, nothing else is free to vary. To me, that's I guess, the easiest way to understand degrees of freedom. We've been using it before. When we did it with standard deviations, the reason you had n-1 is, suppose you knew the mean, and you had 6 numbers. Well, if you know the mean, only 5 of those are free to vary. Once you know the other 5, you can just compute the other one. To me, it's true. That is degrees of freedom when you do means, but this is just easier to explain. So, based on this example data too, do you think you can conclude that there is a relationship between gender and car color? Here we said there is a relationship because these are far away from what you would expect if there's no relationship. But these are pretty close to what you would expect if there's no relationship. Therefore, I'm not going to reject HO. I'm going to conclude that there might not be a relationship. Again, because the numbers here are reasonably close from here. You're going to expect, if there's no relationship, that there's going to be some sampling variability, sample to sample. If we went to another place and there were 100 males and 100 females, and we had the same numbers for red, white, and black, you're not going to get exactly 30-30 every time if there's no relationship. That varies some, but 32 and 28 are pretty close to 30 and 30. 51 and 49 are pretty close to 50-50. And 17 and 23 isn't that far from the 220s. So the way the chi-square test works, and we're going to write a formula and everything, but the way it works is we have our observed data. We can figure out what we would expect if there's no relationship. So, if it's this one, example 1, we just compare this to what we would expect if there's no relationship. If they're close, we say there might not be a relationship. If it's far away, we conclude there's a relationship. And again, these are pretty far away from that. 20 and 40, pretty far away from 30 and 30. So we think there's a relationship, and of course that goes the way. And again, over here too, we compare the numbers here to what we would expect if there's no relationship, if there's no effect. Questions on just the logic of the chi-square test? Okay, then. Okay, I should have done this a little bit. You look at number 1 on the sheet that I gave you there. I'll just erase that. So in this one, you probably have seen this before somewhere, either in your psychology class or maybe on the back of a cereal box sometime. These are actually some famous studies done in the 1950s by a guy by the name of Solomon Asch. And what he would do is he would present people with a line here, X, and then he would ask them which of these 3 lines is closest to X in length. And of course it's A, and anybody can tell that. If you just ask people that individually, like 99.9% of people would get that right. So what he would do, he wanted to look at, he was trying to go counter to an existing theory that said people bow to social pressure. But he ended up this is one of the most famous studies for showing that that people do bow to social pressure. Let me go, if I can, just a little further down here. So what he did was, let's see that we're in that number of, where you had 8 people in a group. So, he would have these people in a group. So here they are. And he gives them that task, and the first person says C. And it's not the line A, he says C. The next person says C. The next person says C. And the next person says C. The next person says C. The next person says C. And this person, who's the only person who's really a subject in the experiment, everybody else is a confederate to the experiment, they're all going to say C. What they want to know is, what will this person say? Will he or she say, it's A, I can tell it's A, or will they go along with what everybody else has said? And in a high proportion of times, he did all kinds of different conditions and so on. In a high proportion of times, I think in the first studies, around 30 or 40% of people said C. A lot of people still went with they could trust their senses, but a lot of people didn't. He tried all kinds of different conditions. This one is number of group members that there were. And what he has here is whether or not they complied and the number of group members. And you might expect, if there were only one other person, you would go ahead and say A. So you might expect that the more people there are, the more likely that you are to comply, although just kind of looking at this visually, it looks like that there's maybe some kind of curvilinear relationship. Not what we're going to look at now. We just want to know if there's a relationship between the number of people in the group and whether or not they conformed. So, right over here, HO and HR. I'm just going to put unrelated and related. We would say that conformance either is unrelated to the number of people in the group, or there is a relationship between conformance and the number of people in the group. So first thing I'm going to do, well, let me go one step back first. I'm going to reject HO if chi-square test is greater than some value. So if I blot out one column of this and one row, there's going to be 4, let me draw this over here, I've got 5 columns and 2 rows. I'm going to blot out one row and one column, 4 numbers free to vary. So the degrees of freedom is equal to 4. And did it say an alpha on there? Yeah, alpha is 0.5. And so I gave you a chi-square table, and we have 0.5 and 4 degrees of freedom. That's going to be 9.49. Another way you could compute the degrees of freedom, this is what I do. I just cross out a row and a column. But another way you could compute degrees of freedom is number of rows minus 1 times number of columns minus 1. In this case, there are 2 rows and 5 columns. And of course, that'll come out to be 4 as your degrees of freedom. So I don't care which way of that you do it. There's just 2 ways. I'm going to do something else now. I'm going to redraw this problem, and on a test, I'll give you more room on this. What I like to do is work everything inside the table. So if you're doing a homework on here, the first thing I would do is make the table bigger. So what I'm going to have here is, and you don't have to do it this way. You can put things in columns. And I think I probably have a video where I show you how to do it that way. I like this way. It keeps me organized. So I'm just going to put up in the left-hand corner of each one of these the numbers that I observed. So this is just the data. By the way, I think that the form that I'm going to use, I'm just going to write it up here now, but I'm pretty sure it's on the formula sheet that I gave you yesterday. Pretty sure. If it's not, I'll bring one later or make it where you can print it off from Blackboard. The formula is this. The chi-square test is equal to the sum of observed value minus expected value. The values I have up right now are the observed values. Sometimes you'll see this F sub O and F sub E to mean frequency observed, frequency of expected. This is how I wrote it. Write it squared divided by expected. So first thing I'm going to do is I'm just going to sum So I just get the margins. I'm just adding up. 20 plus 80 is 100 and so on. And I'm going across in the rows. 20 plus 50 plus 75 plus 60 plus 30. There's two ways you can get the expected values. Now, I'm going to try, it may not be like this on every one of them, to make what I would consider relatively even splits. Like this one, if you go across the number of group members, the 2, 4, 6, 8, 10, I have 100 in each one of those. That means I would expect 1/5, just 20%, of these, of every number in this row to be 235 divided by 5. Same thing in the bottom. Remember before we had a 50-50, now we have 1/5, 1/5, 1/5, 1/5, 1/5. The other thing you can do is you can take the row total times the column total divided by just the overall total for each cell. So like for this cell, you would have the row total 235 times the column total 100 divided by the overall total of 500. And so, let's see, I've lent my calculator here. Is that going to be 47 on the top? Okay, so that's my expected value in this cell. In the next one, it's going to be well, since I have 100 here and 235 there, it's going to be exactly the same. If this weren't a 50-50 split, these would change across here. It's always row total, column total over overall total, but in every one of those on the top row, the 235 is going to stay the same, the 100 is going to stay the same, the 500 is the same. So all of these have expected values of 47. And those have to add, so that's got to be expected is equal to 53. Of course, you could do for that the row total, 265, times the column total divided by 500, and that's going to give you 53. And that's going to stay the same in this problem because you have equal splits in each column. Again, these don't have to be the same like this, but I actually think it's easier to understand what's going on if I do give you an even split. So now what I'm going to do, and I'll write the formulas out, but you guys are going to have to calculate these for me. In this cell, I'm going to have observed minus expected, 20 minus expected, that's just the observed minus the expected, squared, divided by the expected. And if someone would calculate that for me, just take 27 squared and divide by 47. 15.5. I'm just going to circle that because what this is going to be here is 15.51 plus, and I'm going to do this for every cell. So in this one, I'm going to have 50 minus 47 squared over 47, 75 minus 47 squared divided by 47, 60 minus 47 squared divided by 47. And then on this one, I'm going to have 80 minus 53 squared divided by 53. Did anybody calculate this one and this one? I believe that's also going to be 15.51 because that's 27. Yeah, that's no, not quite. That's not true. What is it? It's 15.51? Did you divide by 53? Okay, divide by 53.
13.75.
Okay, so now those of you that are here, maybe you get this one. Do you have it?
Yes,
0.2. Anybody have this one? Now pick one out. Does anybody have this one?
16.7.
This one?
3.6.
Say again?
3.6.
This one?
6.2.
Anybody have this one yet?
Hold on a second.
This one? 14.79.
Yeah.
This one. And this one.
5.45.
Okay. So now 15.51 plus 0.2 plus 16.7 plus 3.6. In other words, just add up the numbers that I circled there. Does anybody have a sum for that?
That's 79.56.
Do I have a second? Does anybody else get the same number, 79.56? If not, give me another number and we'll see. Well, for all of them, all the circled numbers. All of the circled numbers. Yeah. Add all of these and just keep on adding them. Add all of the circled numbers. Okay, we have a confirmation. So we're going to get two of you got it. There's not much of a chance you both made the same mistakes. So remember we said we'd reject if it was greater than 9.49. So 79.56 is greater than 9.49. So we reject HO and conclude that there is a relationship between group size and conformity. And I'm not sure if those are actually the numbers for one of his studies or not. I suspect, well, maybe. I remember looking through numbers for many of his studies back in, I have a minor in social psychology, so one of those classes. Okay, so on your calculators, let me I'm looking now back at these. Oh, that's awesome. The original data for the problem. So on your calculator, there is a button that says matrix. Where is that? It's on the left-hand side. You would have to hit second, and it's right the X minus 1 there. So hit that, second, and get to the matrix. And arrow over to edit. Arrow over to edit. So matrix, edit. And then once you've done that, it asks you for the dimensions of the matrix. We have a 5 by 2 matrix. A 2 by 5, I think. 2 by 5. Rows by columns. Put that in there. Does it look like a... Yeah, okay, that's a 2 by 5. If you mess it up, then just go back and switch it. And now in that matrix, put the numbers that we originally had in the data set, the ones that I have circled here. Got the numbers in? Now hit Stat, Tests, and arrow up or down until you get to the chi-square test. There's two chi-square tests on there, not the one that says GOF. We're doing the test of independence, not the goodness of fit. So you see that? All right, hit Enter. And it should say, is there an A and then a B there? Don't change that. Just go down and hit Calculate. And once you've done that, you should see that you have a chi-square test of about 79.56. Good. So if you're using a calculator, and of course you can get check figures pretty easily there for the whole thing. I mean, just put the numbers for the problem in. Once you put them in the matrix, I mean, the chi-square test is, just don't change where you put those numbers. Just always go over Edit and put them in there. There's another nice thing. If you would now go back to the matrix and let's see, arrow over to Edit again. Now, go back. Matrix, arrow over to Edit, and now arrow down one to option to B and hit Enter. There are your expected values. You should see in this case it's not that hard, but if you had a bigger problem, having those expected values there could be a nice thing to be able to get automatically. You never have to change anything in matrix B. When you put them in A and run the chi-square, it will automatically change the dimensions of matrix B and put in the expected values every time, as long as you leave that A and B in your chi-square test. At this point, I hope you're thinking to yourself, I hope this is worth a lot of points on the test. This is a pretty straightforward problem. It's easy to recognize. You're going to have some kind of 3x2 or 4x3 table. It's just going to have frequencies in there. Two qualitative variables, two categorical variables. And we just want to know if there's a relationship between those two variables. Degrees of freedom, easy to get. Always one-tailed upper. It's always reject HO if the chi-square is greater than. Get the expected values, follow that formula through, do it for each cell, and add them up. This is one of the least missed problems in the course. You know, sometimes I'll say this is one of the things that gets missed a lot. This doesn't get missed much. That doesn't mean don't study it. Work a couple of them, make sure you know how to do it, because I have had people miss it. It's kind of embarrassing to miss this problem. You know, it's not that hard. Plus, you can get check figures really easily. So that's the chi-square test. Questions before I erase this? Yes? You could take the row total. So let's say we're looking for this one right here. You get the row total, 235, times the column total, 100, divide by the overall total. Okay? So row total times column total times overall total. It looks like the problems on the worksheet I've made all add up to be something like 1/2, 1/3, where either the columns or the rows are going to be some kind of even split. If you get to a problem where it's not an even split, I recommend that you use your calculator or a computer. It's kind of like my philosophy on computing standard deviations. The mean should come out to be a whole number. Why get into like just a number pushing thing on your calculator. Other questions on this one? If you prefer things in columns, I'm pretty sure I have a video that does this slightly differently, and I'm probably another one that does it just like this. This is the way I do it. I just like everything in the table there and just easy for me to see. Okay, so now I want to go to simple linear regression. I told you I want to finish as much of the course today as I can, so we're moving a little bit, but okay, so the linear regression t-test. I'm just going to do the new part. On the problems that you have, if we have time, maybe I will do one of the ones off the sheet. On the problems you have, you will need to compute, just as we did from exam 1, so you can go back and review a little bit on that. You'll have to compute the means, the standard deviations, the covariance, and the correlation. Most of you could get that right on exam 1, but that was, 3 or 4 weeks ago. So there you go. You get to review. Partly what you'll get to do is just review for the final anyway. So let's say that I had, an X and a Y. Got some numbers there. And let's say that I have N is equal to 20. And let's say that from that, I compute a correlation of 0.57. So, that just means that here's one number, another one, and we got down to 20 observations there, and we had X and Y on both of them. This could be advertising and productivity, hours of training, advertising and sales, training and productivity, any two variables. You want to know an X and a Y. And so what we want to know is the correlation that we calculated, could that be due to chance? Or is there a linear relationship? Can we conclude that there's a linear relationship between the two? So HO. I'm going to put this a couple of ways. One of them is there is not a relationship. I was thinking about what I wanted to tell you, and then I put down exactly what I didn't want to have. There is not a linear relationship between X and Y. It's not there is not a relationship, because there could be a relationship. The data could look like that's a relationship. It's just not a linear one. Okay? So all we're testing is a linear relationship, and we have one Y and one X. If you want to know what to do when you have 3 X's, then take my other class, and we'll do that. Or another class sometime, multiple regression, what that would be. And so HR is that there is a linear relationship between X and Y. There are a couple of other ways to put this. Remember, the parameter for for correlation was rho. So I could have put HO, I'll just write this here. Let me put it in a different color. Rho equal to 0. Rho not equal to 0. HO is there's no linear relationship. HR is there is a linear relationship. And in this class, we're going to do all of these as two-tailed. you might posit a positive relationship or think that, but if you collected the data and it came out to be a negative relationship, you'd probably still keep that result and say, well, look, there's a negative relationship. So we'll just do them all as two-tailed and be honest about that. Another way to put it, not the way we're going to calculate it in here, but I think I should mention it anyway. And you'll see on your calculator that it does both the row and. They'll also say beta equal to 0, beta not equal to 0. And beta is the slope of the line. So all that's saying is that if the slope is 0, which means you have a flat line, then knowing x doesn't help you. A flat line just means it's the average. So this means the slope is 0. This means the slope is something other than 0, maybe something like that. We're going to reject HO if t-test is greater than some number or less than minus that same number. So now we're just back to the good old t-table, except for now the degrees of freedom is equal to n minus 2, which would be 20 minus 2 in this one, or 18 degrees of freedom. The reason it's minus 2 is you're actually computing two sample standard deviation, one for the x's and one for the y's. So you lose one when you calculate the standard deviation of x, and another when you calculate the standard deviation of y. So let's say we have O5 for our alpha, and we know it's a two-tailed test. So two-tailed, O5, 18 degrees of freedom, 2.101. Now hopefully doing that didn't erase my other screen, but we'll know in a minute. All right. I don't mind how this works. I just wish it would work the same way every day. Would be very convenient. So 2.101. And the t-test is equal to the statistic, R. That's the statistic that we, in this case, is given to us, but which we might calculate from data, minus the hypothesized parameter, rho. So, like so many of the things we've been doing, that's going to be 0 all the time. So, the top of this is going to be 0.57 minus 0. The bottom is 1 minus r squared divided by n minus 2. The square root of 1 minus r squared divided by n minus 2. 1 minus 0.57 squared. I'm going to put parentheses here to remind you that when you calculate, it's not 1 minus r then squared. It's 1 minus r squared divided by, in this case, 20 minus 2. So when your calculator put 0.57 divided square root, it's going to give you one parenthesis, give it another one, and put 1 minus 0.57 squared, close that parenthesis, divide by 18, close that parenthesis, and you should be able to get that. Say again? 0.58? Is that what other people get? That seems a little low to me, but maybe it is. 2.94? Someone else try me. That sounds better to me, to be honest with you. But it could be something else. Can we give it a try? .57 / square root. It opens one parenthesis, open another one. 1 minus 0.57 squared, close parenthesis, / 18, close parenthesis.
Got 0.193.
Give me that calculator. Here we go. 2.9, 2.94, 2.94, 2.94. Let me see what you have in your calculator. Okay, you only have the bottom part.
Or the top part disappears.
Yeah, you don't have the top part there.
That makes sense.
Okay, there we go. Anybody else want me to? 2.94 is greater than 2.101. Reject HO. Conclude there is a linear relationship. In this case, between X and Y. Of course, if you had advertising and sales, you would put that instead of X and Y. And that's all there is to it. Other than you have to review and remember how to calculate the means and the standard deviations and the covariance and all of that. Which I think I'm going to let you just review that on your own. I think that actually might be more valuable than me just working one right now. I'll work one next week, but I'd like for you to give that a try. Let's say that that when I had worked this, that X was hours of training, and this was productivity. We've concluded that the data we have is very unlikely to have occurred by chance. Okay? We're going to have a really low p-value. We've rejected HO. We've concluded that there's a linear relationship. Should you now go out and say, let's give people more training? The answer is maybe. Based on my personal experience with training programs, I would say, well, hell no, this can't be true. What you have, we've talked about this before. Correlation tells you if two variables are associated, you still have to think to understand whether or not that relationship is causal. For example, there could be another variable that we may not have even measured it here. And that would be how long, or one example might be, how long the person has worked at this company. The longer they've worked here, just because they've been here, they've had more training. And maybe that experience has made them more productive. So there could be something else causing both of them. It may not be, you can't say on the basis of this that X caused Y. It might. You have to reason through and think about whether or not that makes sense. And it might. But there could be other variables. So be really careful in how you interpret that. And I can just say, whether it's this stat class or any stat class that you might ever take in your life, if you see the word causal, you should be did X cause Y? The answer's no. Now, to me, if you want to get to causation, if you have a randomized experiment, if you could randomly assign people to each one so you had different experience levels and that, I don't think you can really do that in this, but if you could randomly assign people to have this much experience and everything else, then maybe you could. Even in something like historically, the connection between smoking and cancer. It wasn't one study, it was many, many studies before just about everyone, including the cigarette companies, admitted there is a relationship. In fact, one of the two or three, maybe the most well-known statistical theoretician, the person for whom the F test is named, Sir Ronald A. Fisher, believed that there was not a relationship between smoking and cancer. Of course, he smoked and wanted to continue smoking and everything, but and he's dead now. Probably, I don't know if he died from cancer or not, but I know he did hold on to that for a long time. He would say, well, it's just a correlation, it's just an association. That doesn't mean there's a causal thing. But I think finally there were so many studies and so many different types of studies that everybody came along by now. So be careful of that when you're interpreting these, a causal kind of thing. Another thing to be careful of is that, let's say that this was 10 hours and this was 50 hours, and here's our data. We've got a nice, strong linear relationship in there that you can only predict, even if you're just using this for prediction, which still would be relevant, whether or not there's a causal relationship. You could say, well, if somebody had 40 hours of training, we would expect them to have whatever level of productivity that is. Just put it into the equation we'll let our calculator get, which we've done before. Y hat is equal to A plus BX, where A is the intercept and B is the slope. But if someone had 100 hours of training, you would not want to use that equation. Let's say that we came up with Y hat, which is productivity, equal to A plus BX, and we had, let's say, 30 plus 1.4x, which would mean that if we extrapolated back down to here, that we'd have 30 for productivity, and that for every hour of extra of training, your performance would go up by 1.4. At 100, well, is training likely to have some cutoff, like more training after some point might not do you any good, even if it was the cause of it? Maybe. You should not extrapolate beyond the data for which you have observations. All of our observations are between 10 and 50. It could be that flattens out. And you wouldn't want to extrapolate out to here. So don't go outside the data that you have. Now, you have to sometimes at least go out some, because one of the things that you use regression for would be let's say, sales, and month. Now think about this. All of your hiring and budgeting and everything is based on what you forecast sales to be. So you have to go to the next month or 2 months down the road. So, if we had data for months going from, let's say, January of 2011 up through July of 2014, and that's all of our forecast. Let's say we have something like that. Well, we might not expect that to go on forever, but if we're making next month's forecast, we have to assume it's going to go on that far. We might be wrong, and then maybe some other way of forecasting would be better. But we have to have some forecast, and if it's been working in the past, let's assume that it is. Now, I wouldn't want to make a forecast for July of 2016 right now, but making one for August or September this year. There's going to be some error. Of course, there's going to be some variation around that anyway, but in those cases, you have to go somewhat outside the values that you have for X. But be careful about that. It's called extrapolation. Let's do one more thing today. Let's look at number 2. I'm sorry, the second number 2. Sorry about that. I'm not sure what I should have hit the continue numbering thing, but I went from 1 to 4, and then I don't know how this happens, from 2 to 3, no 4, and then on to 5. You guys have tried numbering with Word before, right? You have to be kind of careful, and I did this morning, just putting those together, and forgot to hit the continue numbering. 2 3s, 2 2s. Now we'll have to be careful about that with the assignment. But anyway, so the second number 2, the one that has hours of training and productivity. If you would have your calculators now and put those numbers into list 1 and list 2. So in list 1 you would have the 17, 26, and so on. I'm seeing something. On those last 3 problems, apparently these were from earlier in the semester. So let's add a part D to all of these, which would be, is there a relationship? There's no hypothesis testing there. Let's use alpha 05 for all of them. So on the second two, the one I'm looking at now, the hours of training, and on the next 2 pages, let's make those alpha 05. Is there a linear relationship between whatever the 2 variables are? So do you have the numbers in your calculator now on list 1 and list 2? So let's go stat, test, arrow up to len, reg, t-test. And X would go in L1, Y would go in L2. And then it's going to be a 2-tailed test. I don't think there's anything else you really have to tell it, is there? Where the data are.
Whatever reg uses.
Don't change the frequency thing. That's it. Tell it where your data are and select not equal to on the hypothesis, and then go down and hit calculate. And down at the bottom of there, you should see, well, first of all, you see a t-test up there near the top. You see a p-value. We obviously won't calculate p-values for these, but there's by hand anyway, but there's the p-value. You go down to the very bottom, there's A. That's the slope. The intercept. And arrow down 1 from there, and you should get B. That's the slope. And keep on going, and you should see R. That's the correlation. So now you have check figures for a check figure for part A. You can check to see, this is going to be a homework problem, but you could go ahead now and write down that the t-test is going to be whatever's on your calculator right now, and that the correlation is whatever's on your calculator right now. Now, did everybody get an R of 0.7317? I'm just checking to see whether this guy got his numbers in there right. A t-test of 2.629? Well, I better check your work. Well, you've got some extra numbers in here.
Really?
Yeah.
They might have been stored in there.
Yeah, I guess so. There's no 21 and 18 in there.
Oh, yeah.
You should probably clear those 2 lists out. Let me see what you have. Okay, everybody got else got a t-test of 8.14? Okay, cool. Yeah, I would just routinely clear out the lists before. You just go up and highlight and hit clear. There is a way to clear all of them at once. On the first screen there, you go down and clear list and L1, L2, L3. It's just as easy, I think, just to clear one at a time with the clear. So there's your check figure for correlation. Now if you would do stat calc, and actually you could just do 2 var stats. And if you had, now you should have 2 var stats on your line on your calculator. Since you put them in you could put L1, L2, but if they're in L1 and L2, that's the default. So you could just put enter. And now you should have an X bar. Is that a whole number? Yay. And now there's your standard deviation check figure on there. If you arrow down a little bit further, you'll see Y bar. Is that a whole number? Good. And then there's a standard deviation for a check figure there. So the only thing, when you're working through that correlation, you need the means, the standard deviations. You'll need to calculate the covariance. That's the only one you won't have a check figure for. And then the correlation. Of course, if you get the 2 standard deviations and the correlation, then you've got the covariance. So I think for homework, let's try that one, right, number 2 right there, the hours of training and worker productivity. And then on the previous page, number 3, the favorite beverage and demographic group. And so number 3, obviously, that's a chi-square test. See, you can tell from there, right? You're about 6 or 8 feet away. That's a chi-square test. 2 columns. You should be able to tell from there. That is a linear regression. If there was a 3rd column on this, then you would know it was an ANOVA. Okay? I probably, well, that's it. That's what I have for today. I think there's one thing that I covered last week, but I did not put on this test. So I'm not even sure if I posted the video yet, but I will repost that. It was the sample size thing, margin of error. Okay, so we might have a couple of mop-up things next week just to make sure concepts, if there's something that we didn't do. Other than that, we're going to do some computer stuff. I'll be putting the assignment and posting some videos, and so next week on Monday, Tuesday, and Wednesday, we'll spend some time on computer stuff. Probably 15, maybe 30 minutes a day. Maybe not even that much, but we'll see. Partly what I'll do is I'll give you an assignment, and then if I'll give it to you Monday, you'll try it. If you're having problems with it, then Tuesday I will expect questions during class. And same with Wednesday. So probably I'll show you how to do things on Monday. There was some yesterday as well. And like I said, I have some videos posted now and many more that can be used. And there's another place up in, I think it's Central Michigan, that for SPSS has a bunch of videos. We're not going to do that much, so I don't think it's going to be that difficult. But I do want you to get the assignment, try things, and then we'll have the first part of Tuesday and Wednesday will be questions. The first part of Monday will be just me going over some stuff. Then we should have around an hour or so every day to review stuff for exam 4 and the final. I'll bring some problems. You can bring questions away. I have a little bit of trouble with this. In fact, if there's something that specifically right now you feel like, okay, I'm having a little bit of problem with understanding something in the 2 proportion z-test, then please email me questions over the weekend, and those will be the first things that I cover on Monday. Some of you may be retaking either exam 2 or 3 on Monday. It would be appropriate for you to send me a question over the weekend that says, I'm having a little trouble with that 2 proportion z-test. Could you kind of hit that again Monday? And so use that as a last gasp of getting ready for retaking the exam on Monday afternoon. Again, if you don't need to retake it, obviously you don't have to worry about that. And some do and some don't.